So
Yeah.
okay, so good morning and welcome to the final week of the semester. We made it, and it's a great privilege and honor to have Yair Glasner from Ben-Gurion University of the Negev, and he's going to talk about Boomerang subgroups and Nevo-Stock-Gemma theorem.
Hi, good morning. Thank you. It's really been lovely here. So I'll give it's like a three session course on Boomerang subgroups. I actually sent in the morning to Tatuamasi some notes that I prepared at least for the first two talks. I hope I can finish something for the third one before it actually happens. So it might be helpful if you want. Good, so let me start a bit with the setting. Well, it's all about groups, so gamma will always denote, will be a countable discrete group. G locally compact, second countable, and we will often be interested in the setting where gamma inside G is often a lattice. And somehow the whole kind of theory of rigidity and so on talks about the connections between these two, how, kind of a discrete, so a lattice, namely a discrete and cofinite in the sense that, well, G mod gamma carries a G invariant probability measure. So in a way, gamma is a small subgroup because it's discrete, but it's large also because it captures somehow a significant proportion of the group. And somehow a guideline is that gamma is going to mimic interesting properties of the group G. So this is from the group theoretic point of view. That's going to be our notation. I'm also going to talk about dynamics, and I want to emphasize three different settings. One, I will denote it by X gamma. This is called the gamma flow. Namely, the discrete group gamma acts by homeomorphisms on a compact space, actions by homeos on a compact space. Most usually it will be metrizable. And this is what is called topological dynamics, okay? I'll also talk about measurable dynamics, denoted like this, where this is a kind of a standard Borel probability space, and gamma acts on it by measure-preserving transformations, acts by probability measure preserving transformations. But I'm interested also in a different setting, a slightly more general setting, and this is the setting where the gamma action preserves not only doesn't really preserve the measure mu, but it preserves just the measure class of the measure mu. So a more general setting is, I'll denote it by X, B, mu, gamma, with a kind of a bracket to denote the fact that here gamma preserves just the measure class of a probability measure mu, namely gamma pushes forward mu to a measure which is mutually absolutely continuous with respect to its translate. It's kind of canonical to assume that it's a probability measure, but notice that this also subsumes all the setting of, for example, infinite measure preserving systems, right? Because if I'm just interested in the measure class, I might always normalize it to be a probability measure, but it's not, it's actually a much richer setting. So in order to kind of better understand this setting, let's first focus, and this will be somehow my point of view throughout, you will see how. Let's try to focus on the very interesting but simple case where gamma is Z. So consider, in particular, Z, and then I'll always denote the generator by big T actions. So here is a kind of an interesting theorem in this setting of Hopf. There is a canonical decomposition of X as a disjoint union of two invariant sets. One of them is called the conservative part, and the other one is called the dissipative part, but let me kind of write it as the following. So the dissipative part is just the disjoint union of the translates of a given set, which is kind of called a wandering set. I mean, you can kind of imagine your space as divided into two parts, and here is a wandering set that's kind of dynamically not very interesting. It's just the disjoint translates of some measurable set that T takes from one, just acts on them as a shift. And here, the action of gamma of T on this part is called the conservative action. So where let me write where the action, the system C mu T is conservative in the sense that it satisfies the following equivalent conditions. There are kind of a few different ways in order to view conservativity. One of them, I want every measurable set here should not be like this, it should return to itself. So for every A in the measure algebra of positive measure, there exists some n such that mu of A and its translate is still positive. You can make this even more apparent by saying that mu of A minus the union of n t minus na is equal to 0 for every A. Maybe a different way to view this is to say that if A is contracted, namely T inverse of A is contained in A, then there's not much in the middle. It's kind of it's a non-contracted non-contracting system. Namely, the difference here has to be of measure 0, and for every wandering set is null. In wandering in the sense of this sense, okay? And then this partition, this Hopf decomposition is kind of canonical in the measure theoretic sense of the word. I mean, of course you can take any point here and add it to the wandering set if you want, but measurably it's well defined.
If you want A to be in C, or
Sorry?
you stated this for every B, for every A and B. It would be the system C somehow.
B is the
B is the measure algebra.
You cannot. Yes, it's okay.
Yeah. It's supposed to be a curly B. So let's talk about a few ways in which this, I mean, when do conservative systems actually come about? Examples, or the main reasons somehow for conservativity. So an action is called conservative if it satisfies these equivalent conditions. Actions. Well, the first and foremost example is what is called Poincaré recurrence. Whenever the action is actually probability preserving in the sense that it preserves actually a measure, so one, Poincaré recurrence, every probability measure preserving action is conservative. It's a very deep and very useful fact somehow, but the proof in this setting is trivial. I mean, not trivial, but it's easy, right? I mean, if you have a preserved measure, then every wandering set, a preserved probability measure, every wandering set should be a null set, right? I mean, the total measure of its translates cannot be, I mean, it's just it has to be 0. Another setting which makes rise for conservativity is the periodic action. All orbits are finite, or almost. All orbits are finite. And the third setting which implies conservativity is ergodicity. Well, except for one single counterexample, but if the action is ergodic, and non-atomic space, then it is conservative. Well, I mean, one example of an ergodic action, measure class preserving, is just look at T acting as a shift on the integers, right? That's kind of a counter example. It's definitely not conservative. It's an infinite measure preserving system. So this is an ergodic non-conservative action, but that's basically the only example that you have. So you know, somehow conservativity says that in a way, if you look at this example, for example, what it basically means is that if you look at a positive set, that almost all points eventually return to that set. But in the measure theoretic setting, this is something that is really not very well defined. I mean, because we don't really have points in these, in this measure theoretical setting. And I want to kind of try to translate this into the topological dynamical setting in order to make kind of a better, more deterministic sense of the word, not just almost every. And this will be our kind of main, so in a conservative setting system, if A is a positive measure set, almost every x in A returns to A infinitely often. I mean, we just said that it returns, but of course it will keep doing that. But I want to kind of try to make a more deterministic version of this. So here is a definition. Let X gamma be a topological dynamical system. Then a point X in X will be called a Boomerang point well, I want to say that if it returns infinitely often, or at least once to every, I mean, kind of if it returns infinitely often, but returns under what element and returns to where. And the point is that since we have here a metric structure and a countable group, we might require everything, okay? So, or at least in the topological sense of the word. So it is a Boomerang point if for every gamma in gamma and open neighborhood of X, we have that gamma n of X comes back to U for some, and hence also infinitely many times n in n. So since we're in the topological dynamical setting, we have a canonical collection of sets, just the open sets. It's a metric space, so we have a countable basis for open neighborhoods. It's, in order to satisfy this condition, it's enough to check it for a countable number of open sets. We have a countable number of group elements, and therefore we can kind of canonically define what does it mean to return to return arbitrarily close to the point, and it's kind of a direct corollary of what I just said, that every gamma invariant measure mu on gamma invariant measure mu, a probability measure on X, is supported on boomerang points. So mu, let me write up there. I kind of denote, I denote the collection of all boomerang points in this system by boom of X gamma, and for every invariant measure, the measure of this set is going to be 1. I'm not claiming that this is a closed set, so it's not a support in that sense. I mean, if you think about it for some time, you can convince yourself that actually it's a G delta set, but it definitely doesn't have to be closed. But kind of it's an outcome of everything I just said, that this actually happens. So let's prove this.
Excuse me, to clarify, you define this for arbitrary discrete group gamma or just for the actions? Because here I think you were talking just about actions previously.
So I kind of, okay, sorry, maybe I did not clarify. I made kind of a detour to explain what conservativity is, and talked about z-systems in that setting, okay? Because conservativity somehow is defined in terms of z-systems. Now, if you do topological dynamics, you know that just as well you can define conservativity also for group actions by requiring that there is some group element that will bring almost every point back to a positive set. This is not what I'm interested in, okay? I'm interested in now in systems, topological, dynamical, or measurable, which are going to be point-wise conservative in this kind of sense of the word. Not that the action of the whole group is conservative, but that the action of every single group element is going to be conservative in its own right when you consider it as a separate z-system. Okay, and this is exactly what this definition is trying to capture. Okay, it's trying to capture in the topological dynamical sense some kind of notion of when every single point, every single group element, points where I'll give a definition, but I'm just trying to frame the setting in which I'm interested.
And the group is not assumed to be torsion-free, right?
Sorry?
Gamma is not assumed to be torsion-free, right?
Gamma is not assumed to be torsion-free, yes. So
something interesting.
But notice that this condition somehow is automatically satisfied for every torsion element. In In fact, if you act with the torsion group, then all points are going to be boomerang points, and the theory somehow trivializes in that case. And there are ways in which to remedy that, but let's not get into it right now. So these boomerang points, which are going to be our main protagonists somehow, they are kind of very interesting points, because these are exactly the points that invariant measures see. They are, if you ever deal with a dynamic, but they are universally such. If you ever deal with a dynamical system and you want to know how a typical point looks like, but without having an invariant measure, well, these are these boomerang points, because once you put an invariant measure on the system, regardless of the measure, it's going to see only these boomerang points. And that's kind of the essence of this theorem. And the proof of this is just from Poincare recurrence. Namely, let us enumerate the pairs gamma u, where gamma is in gamma and u is in some countable basis for the topology. And by Poincare recurrence, gamma nx comes back to u infinitely often for mu almost every x in u. It might happen that this specific measure that you chose actually renders u to be a null set. I don't care. In this case, it's really not significant what happens in this set. But this is just what Poincare recurrence says, right? And if u is a positive measure set, then almost all points will come back. And now we just intersect over this countable collection. And now take the intersection over all sets. So over all sets and group elements. So let's try to recast this in the measure theoretic setting. So definition, non-singular system I call this a non-singular system. Okay, where non-singular refers to the fact that only the measure class is preserved, not the measure. It's called EC, and here I'm trying to capture exactly what you were asking. It's called an element-wise conservative system if every group element, gamma and gamma separately, is conservative. And similar to what we did in topological case, or in the Z case, let's give a few conditions where, a few sources for such actions. So examples. One, every probability preserving action is element-wise conservative just by Poincaré. Once you have an invariant measure, then right, this is still here. Once you have an invariant measure, then it's necessarily conservative, and the measure is invariant under all group elements. So this is basically the canonical way to do it. Also, if you have, as you said, if you have a periodic group, or more generally, if the action is periodic, so element-wise periodic actions where almost all orbits are finite, for every element separately, and to begin with, it's not clear that it's not clear somehow that there are more examples somehow. It seems like an abstractly defined generalization of probability preserving setting, but it's not so clear that there are interesting examples, but it turns out that there are. So one theorem that I will try to talk about in the last lecture, by the way, all of this is joint. It's kind of based on two joint papers. So one is with Waltraud-Lederle, and the other is with Lederle and Tobias Hartnick. So this theorem is from the second paper, namely there are uncountably many non-equivalent actions, element-wise conservative actions of F2 that are not probability measure preserving. And what will be kind of crucial in our setting is that these can be taken to be non-free. And I will get back to that in just a few minutes. I'll tell you why this is important. Okay, so I'm going to get back to our group theoretic setting and try to say, what we can add in terms of this theory of rigidity or connections between the lattice and an ambient Lie group that I was alluding to in the very beginning. So first let me quote kind of the motivating theorem for everything that we are doing. This is, I call it the Nevostak-Wimmer theorem. And let me, for the sake of this lecture, maybe tomorrow I'll try to widen up the scope a little bit. But for the sake of this lecture, let me try to give the very simplest possible version that I can talk about. So I'm talking about just one kind of ambient Lie group. Let G be the group SLN R. And this is, as many of these things go in rigidity theory, it's going to be a higher rank group in the sense that it has a high dimensional abelian diagonalizable subgroup. Gamma inside G a lattice, then every probability measure preserving action X B mu gamma is either essentially free. This is like, the best way that you can be free from, in the measure theoretic setting. You can say that the stabilizer of every point is trivial, but of almost every point, and it doesn't even make sense. Or the action is actually transitive on a finite set. Namely, it's just gamma acting on the cosets of some finite index subgroup. Sorry, every ergodic. Of course, if I don't require ergodicity, I can take always convex combinations of these things. So this is kind of a very striking theorem. It really shows that these groups, in a fundamental way, they don't admit any very interesting non-free actions, kind of contrasting with what I just said here. Okay.
What does it mean? Transitive on a finite set?
So this is i.e. gamma acting on gamma mod delta, where delta is some finite index subgroup with the counting, with the normalized counting measure. Okay, I mean, this group is residually finite, it has many finite index subgroups, it has finite actions on finite sets. And this is definitely a probability preserving action, which is non-free. It's also very far from being faithful, because if you're acting on a finite set, there is a normal subgroup still of finite index that actually fixes everything. This is obviously an option. I mean, you can't rule that out. And every other action, which is really a probability preserving action in the sense that we're used to, is actually essentially free. So our theorem, the one that I want to discuss in the first two talks, is to generalize this theory to the element-wise conservative setting. So instead of, I mean, there's been a lot of work actually in trying to generalize this theorem in the way of generalizing the acting groups. I mean, and I'll talk about that. And it's still, some very significant research is being done in this direction. But now I want to try to generalize the setting of the action. So this is a joint theorem with Waltraud. Assuming that we need a new that the Q rank of gamma is at least 2. So I'm kind of giving a new restriction on the group, on the lattice that is acting, not just that it is higher rank in the sense that the group is SLN, but I want it to be also in the level of the lattice. It has to somehow be of higher Q rank. Then the same dichotomy holds for element-wise conservative actions. So if this theorem says that there are, that F2 admits many interesting element-wise conservative actions that do not come from the probability-preserving setting, even in the non-free realm, then here what our theorem says is that basically, well, if you are talking about non-free actions, at least it's all that we have. And it's still an open question whether actually this group does admit interesting element-wise conservative actions that are essentially free. That might very well happen. But this is what we can prove. So let me just give an example. Right, are we taking a break at the hour, I say? Or? Yeah, okay, so before the break, let me just give an example to, to illustrate what is this higher Q rank additional assumption that we have. So example, gamma is SL4V inside SL4R, also 3, but is of, so Q rank of gamma is 3. Okay, and it's kind of a nice exercise. Try to find a 3-dimensional abelian diagonalizable subgroup inside this SL4V. So our theorem definitely works for this group. But here's a situation where it's
Why are you avoiding SL3?
Sorry?
Why are you avoiding SL3?
No, I just want to contrast it with the SL3 is also. I just want to contrast it with the second example that I'm going to give, and it's also going to be in SL4. Namely, consider the quaternion algebra let me call it H23. So this is kind of generated by H23 is generated by 1, I, J, and K, where I squared is 2, J squared is 3, and Ij is me minus Ji is okay. It's kind of a four-dimensional algebra, very similar to the regular Hamiltonian quaternion algebra, only I'm taking different constants here. It's an algebra that is defined over Q. And in kind of formal terms, this algebra splits, unlike the regular quaternion algebra, splits over R. So over R, this algebra is just isomorphic to the 2 by 2 matrix algebra. It's not a division algebra. Over R, just by sending I to square root of 2 minus square root of 2 and J to square root of 3, square root of 3, you can check that this is an isomorphism. And in fact, what is spanned by these two and the identity is just the whole matrix algebra. But it ramifies over Q. So over Q, if I just look at the Q points of this algebra, it is going to be a division algebra. Okay, so if you know this Margulis theorem that all lattices in SL4 are arithmetic, and if you're not so much into the theory and you ever kind of wondered, okay, if they're all arithmetic, why aren't they all SL4V? Well, here is an example. What you kind of do is define a completely different algebraic group, but whose R points are the same as the points of SL4. Namely, consider the algebraic group G, which is just the units of this quaternion algebra. I'm just looking at all the quaternions that have all the Z, such that Z times Z bar is 1, that have kind of a reduced norm 1, and this is a nice algebraic group whose R points will just be the SL4 of R. Whose R points will just be SL2 of R because over R this is just the matrix algebra, and I'm taking basically here just these elements that have determinant 1. But over Q, this algebra is a division algebra, and there is the ones that appear here are just going to be 1 and minus 1. They are central elements. So if I consider now G, so I'm considering now SL two of this quaternion algebra H. So this is going to be, if I take now this to be maybe my group, what's a good name for a group, L, then now L of R is just SL4 of R, but L of Z, well, you can think of it as kind of 4 by 4 matrices, A, B, C, D, where A, B, C, D kind of represent quaternions in this sense of the word. And now I'm looking at only integer values of these quaternions. So the center, this is going to be a lattice inside SL4, but the center of this will require a diagonal thing where A and B are quaternions whose product is 1, and this can only be one-dimensional center. So this is kind of a nice example of a group that we do not know how to handle. It's an example of a lattice inside SL4 that has Q rank 1, and that doesn't fall into the jurisdiction of this theorem. Good, so I say it's a long talk, right? So should we have a small break? Or,
So we met at 10:11.
10:11, cool.
Yair, what does ramifies mean?
I already know.
I mean, for quaternion algebras, there is this whole theory of central simple algebras. But for quaternion algebra, there are basically two options over any field. It can either be isomorphic to the matrix algebra or it's a division algebra. And these are just called split and ramified. Split means the matrix algebra, and ramified means the division algebra. So maybe just two remarks. One, Bashir asked me over the break about Negev here, because often it's known as the Stack-Wimmer theorem, and I somehow feel that Negev should be added here. I mean, the story is like that. Stack-Wimmer had this beautiful paper proving this theorem, and they relied on an older theorem of Wimmer himself, which is called the intermediate factor theorem. Kind of generalizes Margulis factor theorem. And this term eventually turned out to be to have a mistake, that paper, which was eventually corrected. I mean, the mistake was found and eventually corrected by Negev and Zimmer. And therefore, I think it's kind of due to include Negev in that theorem. But if you look in the original paper, then you see it's just Stack and Zimmer, okay? And but there is kind of a whole theory of Negev and Zimmer that eventually manages to prove the intermediate factor theorem only after, way after that. I mean, another kind of, the example I kind of gave with the quaternion algebras is an example of a lattice that is of Q rank 1. But kind of also, I should mention that a striking setting in which our theorem does not hold and kind of stands out is the whole realm of co-compact lattices, which are exactly these of Q rank 0. Kind of a quiz. I mean, the analytic characterization of being co-compact is equivalent to the algebraic characterization of being of Q rank 0. So, okay, so all until now it seems like completely a theorem in dynamics. But in fact, what I want to claim, and this is going to be the guiding idea, is that in fact it's a theorem in group theory. And this is already implicit in the Stack-Wimmer original paper, which essentially kind of implicitly already defines this notion of invariant random subgroups and talks about them, not with this name, but so This is in fact all just group theory, and the proof is kind of algebraic, or at least the proof that we bring. And I want to try. So I'm not 100% sure to what extent people are familiar with invariant random subgroups. If I should. I mean, I'll talk, but I was not 100% sure what the audience is. So I mean, if it's boring for you, just push me. Let me know. And I'm, just for simplicity, I'm going to discuss this whole setting in the discrete case, because this is what is going to be applicable to us. So let gamma be a countable discrete group, and I'm looking at the collection of all subgroups of gamma. This is all subgroups of gamma. Well, I can kind of topologize it by embedding it into the collection of all subsets of gamma. And, it's an easy exercise to check that this is a closed set. And since this is naturally a Tikhonov space, just a Cantor set, then this is also a compact metrizable space. So this is a compact metrizable totally disconnected space, and gamma acts here by conjugation. Don't mistake and take the left action, right? I mean, when you think about the natural action on this space, you usually think about translations, but translation takes a group to a coset, and here I get the natural action is by conjugation, and this makes this into a topological dynamical system. This makes sub gamma into a gamma flow, a topological dynamical system, in the sense that we've been discussing just now, and I mean, if you haven't seen it, work out the exercise. Right? This is closed. This action is continuous by homeomorphisms and so on. Now, definition: an invariant random subgroup of gamma is a gamma invariant Borel probability measure on sub gamma, and a Boomerang subgroup is a Boomerang point in this system, sub gamma, and we denote boom gamma the collection of such subgroups. And by the general theory that we were discussing, every IRS is actually supported on this nice G delta subset fitting inside the collection of all subgroups of gamma. So examples. One, let's take the delta measure on every normal subgroup. Here is sub gamma. Of course, every invariant point carries an invariant measure. Also, every finite orbit carries an invariant measure. So, if I have, what does it mean for a subgroup to have an invariant, a finite orbit? It just means that its normalizer is of finite index. So if gamma, the normalizer is of finite index, then I can take the sum over all the delta measures on these various. I mean, if there's a finite orbit, what I'm saying, in particular, if the group is of finite index, then it carries the finite orbit carries an invariant measure. Kind of a more interesting example is the one that comes from ergodic theory, right? So if x, b, mu, gamma is a probability measure preserving action, so here is x, and here is sub gamma. Well, one way to you can think as a measure theorist, or you can think as a probabilist, right? So for probabilists, an invariant random subgroup is just a random subgroup, right? It's not some measure or something. So if you have an ergodic theory like that, the natural thing that you can do is, just close your eyes, hit the place at some random point, and take the stabilizer of that random point x. And of course, the natural fact that the stabilizer of gamma x is just the conjugate of gamma x means that this is invariant under the action. More formally, in a measure theoretic setting, you can look at the stabilizer map. And for every point here, just take its stabilizer, and then I push forward. This gives me a map. This kind of realizes sub gamma as some kind of a universal factor for every dynamical system. And you can just push forward the measure here to obtain an IRS on the space of invariant of subgroups. Now, of course, if you do classical ergodic theory, then your actions are essentially free usually, and this will all be trivial. The image here will almost surely be just supported on the trivial group. But if you start discussing non-free actions, then this gives a kind of a powerful tool in ergodic theory where you can somehow separate the dynamics and also the subgroup, the kind of the group theoretic content is somehow captured inside this factor. So if this is a probability measure preserving action, then let me just write it formally. If you look at the this is a probability measure on sub gamma. This is an example of an IRS, and in fact this is universal. It's a theorem of mine with Abert and Virag that says that every IRS can be realized in this form. In fact, any IRS can be realized by such a construction. And let me go ahead immediately and generalize this. If X, B, mu, gamma is element-wise conservative, then mu star, stabilizer, if you push forward mu by the stabilizer, almost every subgroup is Boomerang. Or in other words, almost every stabilizer of the stabilizer of almost every point in an element-wise conservative action is a Boomerang subgroup. So in this, in this kind of setting, we can recast the theorems that I just said. So recasting the above theorems, Nevos-Stack-Zimmer, so gamma inside G as above. Okay, I can talk about a lattice inside SLN or if you want simple high rank Lie groups. And I'll get to it tomorrow. I'll start opening up and with more examples than just SLN. But in this setting, every invariant random subgroup of gamma is either trivial or of finite index. And our theorem says that assuming...
You mean finite, sir?
Yeah.
You got it back.
Sorry.
Yes, no?
Is either finite central. I mean, these lattices, it's a simple setting, but as in the Lie group thing, right? A simple group doesn't mean that it doesn't have a center. So the lattice might very well have some finite center, and of course, every subgroup there is going to be a normal and an IRS. So you have to allow for that. Assuming that Q rank gamma is at least 2, this is our theorem, the same holds for every Boomerang subgroup. And this is actually what I'm going to prove. And I want to emphasize that in fact this will give a very easy, very streamlined proof of the Nevostak-Zimmer theorem, and hence also of Margulis's normal subgroup theorem, if you are familiar, in this specific case. So we just prove that there are no Boomerang subgroups. So a few remarks.
Can I still ask a question about
Yes, please. Yeah.
about the last comment that you wrote down here? So, but here we are kind of outside of the world of IRSs, right? Because if
Right. Or a posteriori, we are exactly back to IRS as if gamma is this kind of a higher rank lattice. But in general, yes. This is the whole point. It's kind of trying to generalize. I mean, it kind of has a twofold direction here. One is, generalizing the notion of IRS, but also a different direction is that it's really an object of a different nature. I mean, an IRS is kind of a probabilistic object. And Boomerang is a deterministic subgroup. It's, somehow the whole kind of work on boomerangs basically started from our asking ourselves, how does an IRS actually look like? And, what is a typical group if you open it, what is a typical group that actually happens? And we came up with this notion of Boomerang subgroups. And so it has also a different nature. I mean, it's not just the generalization per se. It's kind of a deterministic family of groups that we know do not exist here in this, or not exist, but they are all of finite index or finite. So one remark that I think is in place here is that the Nevostak-Zimmer also has, and this whole theory also has a version in the locally compact case. And this can be stated not for gamma, but this theorem can be stated not for gamma, but for the group G itself. There also there are no IRSs in the sense of locally compact groups. And we do define Boomerang subgroups also in that setting, but we still don't know how to prove it in that case, that even SLNR, say, does not have Boomerang subgroups. So the Nevostak-Zimmer is true also for G, not for gamma. You have to define it. Let me not go through this right now. And it's very interesting. To prove a Boomerang version also there. So good. So let me do a few. Until when do I go? That
10:47.
10:47. Okay. Good. So I want to do some.
Sorry. Yeah, but the usual schedule takes into account the break as well.
I want to start developing some basic theory of Boomerang subgroups. Let's start with noting some basic properties of boomerangs. This is a completely general discrete group, so let delta be a boomerang subgroup in delta. Let me write a few statements. For every gamma in gamma, delta in delta, gamma to the n, delta, gamma to the minus n, falls again in delta infinitely often. 2, for every gamma in gamma, and delta in delta, the commutator falls in delta for infinitely many n and every m. If sigma inside gamma, then delta intersection with sigma is going to be a boomerang in sigma. So if you take a boomerang in the bigger group, you intersect it with a smaller group, it's still a boomerang. If, let's call it big Xi, is some finite extension of gamma, then delta is a boomerang also in Xi. So these are just basic. I mean, it's an exercise. All of these are exercises, but let's do them just to to get a feeling of this theory. So I start with the first one. Here is my space sub gamma, and let me take here a boomerang subgroup and an element delta in delta. Now here is a nice open neighborhood of delta, which I call the envelope of little delta. Okay, so the envelope of little delta is just the collection of all H subgroups containing this little delta. So delta is one of them. I started with an element in delta. It's one of them. And if you think about the topology, right? 0, 1 to the gamma, and I define the topology on the collection of subgroups as embedding here. So containing one single element, if you identify subgroups here or subsets just with their characteristic functions, then containing one element is basically just a cylindrical set. That's a canonical open neighborhood of this point. And the fact that delta is boomerang means that for every direction gamma that I choose in the group, gamma to the minus n, delta, gamma to the n, this is, I start conjugating it by gamma inverse. And so on. Eventually, I'm going to come back. This is just a definition of the boomerang. So gamma minus n delta gamma will contain delta again, which is equivalent to falling inside this open set infinitely often. And of course, conjugating back, I get that gamma to the n, delta gamma to the minus n is going to come back here. That's why I chose the thing. Of course, 2 is a direct corollary of that, because I just write gamma to the n, delta to the m, gamma to the minus n, delta to the minus m. This is the commutator, and since this comes back to delta infinitely often, I mean, forgetting, for example, the m, this comes back to delta infinitely often, and of course, if it is in delta, every power will also be in delta, so the whole commutator fits inside delta. Let's see a nice corollary of this. Let's see a nice corollary in the free group. You know that in the free group, every two normal subgroups, non-trivial normal subgroups, have a non-trivial intersection. Okay, and what is the proof of that? That you just, the commutator is contained in the intersection. So the same thing holds for non-trivial Boomerang subgroups. If delta 1 and delta 2 are boomerangs, non-trivial, then delta 1 intersection delta 2 is non-empty still. It's an open question. If it's a boomerang again, I don't know. I don't believe it is, but I don't have any counter example. And so proof.
Excuse me, a question about what you said.
Sorry?
So you don't have counterexamples just for F2 or in general for?
I mean, it's often I think I have some counter examples in some settings, but I think I do. Yeah, not 100% sure at the moment, but. So here is the proof. Well, this is not trivial, this is not trivial. Take delta 1 in delta 1, delta 2 in delta 2, and believe me for a moment that Boomerang subgroups are never cyclic. So I can take delta 1 and delta 2 that do not commute with each other. And then I start taking these commutators and take delta 1 to the n, delta 2 to the m, delta 1 to the minus n, delta 2 to the minus m. And now let me forget about m for a minute and choose an n so that this whole thing falls again inside delta 2. Okay, falls again inside delta 2. I can do that due to the first step over there. And of course, if this is in delta 2, without m, it's going to be in delta 2 for any possible value of m. And then this whole expression is going to fall inside delta 2. On the other hand, if I put the brackets like that, for any n, I can choose in particular for the n that I already found, I can choose my m in such a way that this falls again in delta 1. Okay, so an appropriate choice of m and n will guarantee that this is actually falls inside the intersection. Now, on the other hand, since these are two non-commuting elements in the free group, they generate a free group in their own right. And no matter what this expression is, it's not going to be trivial. So I found a non-trivial element also inside the intersection of these two Boomerang subgroups. Okay, I don't have much time, so let me just finish this. So 3 is kind of a nice exercise. You can look at the map from sub gamma to sub sigma, which just sends an element H here to its intersection with sigma. And convince yourself that this is a continuous map. Okay, so continuous surjective, of course, and then you know it immediately follows. So this statement follows from the continuity. The continuity and surjectivity of this map. And the third one is completely obvious. Namely, well, if I have here gamma and xi, and let me take delta, some boomerang subgroup here, I mean, I mean, I want to prove somehow that xi to the ni delta xi to the minus ni, this is maybe a different way of phrasing the boomerang condition, converges in the Chaboti space, in the space of all subgroups, back to delta for some subsequence, right? This is another formulation of the boomerang property, and this is for every xi in xi. Well, but of course, if you pick here some xi, then since this is a finite index extension, some finite power of xi is going to fall into gamma already, and then I just take, so xi to the m actually sits in gamma, and then I can just you know, gamma by the boomerang property gamma to the, sorry, xi to the m. I mean, okay, you see what I mean. I just take these to be power. I mean, I take ni's to be chosen appropriate, just multiples of m, so that I'm actually using the boomerang property. Okay, I think I used all of my time. It's funny because I was sitting with Tatuamasi in the cafe in the morning, and he told me, you know, the talk is 90 minutes. And I said, oh no, and I started sitting frantically, scribbling some more things because I thought it's going to be an hour. But I didn't finish even what I planned to do. So that's somehow what always happens. Okay, thanks.
Do you have any questions for Yair? If not, let's thank Yair again. We'll meet in 25 minutes.